This last 60 years, we saw several tectonic shifts in computing where everything changed. And we're about to see that happen again. The further performance we drive up, the greater the cost decline. Hopper platform, of course, was the most successful data center processor probably in history. However, Blackwell is here, and every single platform, as you'll notice, are several things. You got the CPU, you have the GPU, you have NVLink, you have the NIC, and you have the switch. Every single generation, as you'll see, is not just the GPU, but it's an entire platform. We build the entire platform, we integrate the entire platform into an AI factory supercomputer. However, then we disaggregate it and offer it to the world. Our basic philosophy is very simple. One, build the entire data center scale, disaggregate it, and sell it to you in parts on a one-year rhythm, and we push everything to technology limits. Whatever TSMC process technology, will push it to the absolute limits. Whatever packaging technology, push it to the absolute limits. Whatever memory technology, push it to absolute limits. SerDes technology, optics technology, everything is pushed to the limit. Blackwell is here. Next year is Blackwell Ultra. Just as we had H100 and H200, you'll probably see some pretty exciting new generation from us for Blackwell Ultra. This is the very first time, and I'm not sure yet whether I'm going to regret this or not. We have code names in our company, and we try to keep them very secret. Most of the employees don't even know. But our next generation platform is called Reuben. So we have the Reuben platform, and 1 year later we have the Reuben Ultra platform. All of these chips that I'm showing you here are all in full development, 100% of them. And the rhythm is 1 year at the limits of technology, all 100% architecturally compatible. So this is basically what Nvidia is building, and all of the richness of software on top of it. So in a lot of ways, the last 12 years, the company has really transformed tremendously, and I want to thank all of our partners here for supporting us every step along the way. This is the Nvidia Blackwell platform. Ladies and gentlemen, this is Blackwell. This is our production board. This is the most complex, highest performance computer the world's ever made. This is the gray CPU, and these are, you could see each one of these Blackwell dies, 2 of them connected together. You see that? It is the largest die, the largest chip the world makes. And then we connect 2 of them together with a 10 terabyte per second link. And the performance is incredible. Take a look at this. The AI flops for each generation has increased by 1,000 times in 8 years. And just to compare, even Moore's law at its best of times compared to what Blackwell could do. So the amount of computations is incredible. And whenever we bring the computation high, the thing that happens is the cost goes down. The amount of energy that is used has gone down by 350 times. Pascal would have taken 1,000 gigawatt hours. 1,000 gigawatt hours means that it would take a gigawatt data center. The world doesn't have a gigawatt data center, but if you had a gigawatt data center, it would take a month. If you had a 100 megawatt data center, it would take about a year. And that's the reason why these large language models, ChatGPT, wasn't possible only 8 years ago. With Blackwell, what used to be 1,000 gigawatt hours to 3, an incredible advance. Our token generation performance has made it possible for us to drive the energy down by 45,000 times. Okay, so Blackwell is just an enormous leap. Even so, it's not big enough. And so we have to build even larger machines. And so the way that we build it is called DGX. So this is a DGX Blackwell. This is air-cooled, has 8 of these GPUs inside. Look at the size of the heat sinks on these GPUs. About 15 kilowatts, 15,000 watts, and completely air-cooled. This version supports x86, and it goes into the infrastructure that we've been shipping hoppers into. However, if you would like to have liquid cooling, we have a new system. It's based on this board, and we call it MGX for modular. So this one node has 4 Blackwell chips, and these switches connect every single one of these to each other, so that we have one giant 72 GPU Blackwell. This now looks like one GPU. This one GPU has 72 versus the last generation of 8, so we increased it by 9 times. The amount of bandwidth we've increased by 18 times. The AI flops we've increased by 45 times, and yet the amount of power is only 10 times. This is 100 kilowatts, and that is 10 kilowatts. And that's for one. You could always connect more of these together, and I'll show you how to do that in a second. There's this confusion about what Nvidia does. How is it possible that Nvidia became so big building GPUs? And so there's an impression that this is what a GPU looks like. Now, this is a GPU. This is one of the most advanced GPUs in the world, but this is a gamer GPU. But you and I know that this is what a GPU looks like. This is one GPU. Ladies and gentlemen, DGX GPU. The back of this GPU is the NV spine, and it's right here. This is an NVLink spine, and it connects 70 GPUs to each other. This is an electrical, mechanical miracle. The transceivers makes it possible for us to drive the entire length in copper. And as a result, this switch, NVLink switch, driving the NVLink spine in copper makes it possible for us to save 20 kilowatts in one rack. 20 kilowatts could now be used for processing. Just an incredible achievement. So this is the NVLink spine. And even this is not big enough. Even this is not big enough for AI factories, so we have to connect it all together with very high-speed networking. We have two types of networking. We have InfiniBand, which has been used in supercomputing and AI factories all over the world. And it is growing incredibly fast for us. However, not every data center can handle InfiniBand because they've already invested their ecosystem in Ethernet for too long. And so what we've done is we've brought the capabilities of InfiniBand to the Ethernet architecture, which is incredibly hard. Ethernet was designed for high average throughput because every single node, every single computer is connected to a different person on the internet, and most of the communications is the data center with somebody on the other side of the internet. However, deep learning and AI factories, the GPUs are not communicating with people on the internet. They're communicating with each other because they're collecting partial products, and they have to reduce it and then redistribute it. Chunks of partial products, reduction, redistribution. That traffic is incredibly bursty. And it is not the average throughput that matters. It's the last arrival that matters. It's whoever gives me the answer last, okay? Ethernet has no provision for that. And so there are several things that we had to create. We created an end-to-end architecture so that the NIC and the switch can communicate. And we applied 4 different technologies to make this possible. Number one, Nvidia has the world's most advanced RDMA. And so now we have the ability to have a network-level RDMA for Ethernet that is incredibly great. Number two, we have congestion control. The switch does telemetry at all times incredibly fast. And whenever the NICs are sending too much information, we can tell them to back off so that it doesn't create hotspots. Number three, adaptive routing. Ethernet needs to transmit and receive in order. We see congestions or we see ports that are not currently being used. Irrespective of the ordering, we will send it to the available ports, and Bluefield on the other end reorder so that it comes back in order. That adaptive routing, incredibly powerful. And then lastly, noise isolation. There's more than one model being trained or something causes the last arrival to end up too late. It really slows down the training. Overall, remember, you have built a $5 billion or $3 billion data center, and you're using this for training. If the training time was 20% longer, the $5 billion data center is effectively like a $6 billion data center. So the cost impact is quite high. Ethernet with Spectrum-X basically allows us to improve the performance so much that the network is basically free. And so this is really quite an achievement. We have a whole pipeline of Ethernet products behind us. This is Spectrum X8. It is 51.2 terabits per second. The next one coming is 512 radix, is 1 year from now. 512 radix, and that's called Spectrum X800 Ultra. And the one after that is X1600. But the important idea is this. X800 is designed for tens of thousands of GPUs. X800 Ultra is designed for hundreds of thousands of GPUs. And X1600 is designed for millions of GPUs. The days of millions of GPU data centers are coming. And the reason for that is very simple. Of course, we want to train much larger models, but very importantly, in the future, almost every interaction you have with the internet or with a computer will likely have a generative AI running in the cloud somewhere. And that generative AI is working with you, interacting with you, generating videos or images or text, or maybe a digital human. And so you're interacting with your computer almost all the time, and there's always a generative AI connected to that. Some of it is on-prem, some of it is on your device, and a lot of it could be in the cloud. These generative AIs will also do a lot of reasoning capability. Instead of just one-shot answers, they might iterate on answers so that it improves the quality of the answer before they give it to you. And so the amount of generation we're going to do in the future is going to be extraordinary. Let me talk about what's next. The next wave of AI is physical AI. AI that understands the laws of physics. They have to, of course, have excellent cognitive capabilities so they can understand us, understand what we asked, and perform the tasks. Of course, when I say robotics, there's a humanoid robotics that's usually the representation of that. But that's not at all true. Everything is going to be robotic. All of the factories will be robotic. The factories will orchestrate robots, and those robots will be building products that are robotic. Robots interacting with robots, building products that are robotic. In order for us to do that, we need to make some breakthroughs. First, we're going to create platforms for each type of robotic systems. One for robotic factories and warehouses. One for robots that manipulate things. One for robots that move. And one for robots that are humanoid. And so each one of these robotics platform is like almost everything else we do. A computer, acceleration libraries, and pre-trained models. Computers, acceleration libraries, pre-trained models. And we test everything, we train everything, and integrate everything inside Omniverse, where Omniverse is where robots learn how to be robots. Now, of course, the ecosystem of robotic warehouses is really complex. It takes a lot of companies, a lot of tools, a lot of technology to build a modern warehouse. And warehouses are increasingly robotic. One of these days will be fully robotic. Now let's talk about factories. Factories has a completely different ecosystem. A robotic factory is designed with 3 computers. Train the AI on Nvidia AI. You have the robot running on the PLC systems for orchestrating the factories. And then you, of course, simulate everything inside on. The robotic arm and the robotic AMRs are also the same way, 3 computer systems. And we provide the computer, the acceleration layers, and pre-trained AI models. We've connected Nvidia Manipulator and Nvidia Omniverse with Siemens, the world's leading industrial automation software and systems company. This is really a fantastic partnership, and they're working on factories all over the world. And that's the factory, the robots inside, and of course, all the products are going to be robotic. So there are 2 very high volume robotics products. One, of course, is the self-driving car, or cars that have a great deal of autonomous capability. Nvidia, again, builds the entire stack. Next year, we're going to go to production with the Mercedes fleet, and after that, into the JLR fleet. The next high-volume robotics product that's going to be manufactured by robotic factories with robots inside will likely be humanoid robots. And this has great progress in recent years in both the cognitive capability because of foundation models and also the world understanding capability that we're in the process of developing. I'm really excited about this area because obviously the easiest robot to adapt into the world are humanoid robots because we built the world for us. We also have the most amount of data to train these robots than other types of robots because we have the same physique. And so the amount of training data we can provide through demonstration capabilities and video capabilities is going to be really great. And so we're going to see a lot of progress in this area. I think we have some robots that we'd like to welcome. Here we go, about my size. And we have some friends to join us. So the future of robotics is here, the next wave of AI. And of course, you know, Taiwan builds computers with keyboards. You build computers for your pocket. You build computers for data centers in the cloud. In the future, you're going to build computers that walk. And as it turns out, the technology is very similar to the technology of building all of the other computers that you already build today. So this is going to be a really extraordinary journey for us. Thank you all for coming. Have a great Computex.